Hi, I'm Jordan Lloyd Graber. I'm an associate professor at the University of Maryland. For my slot at the Simultaneous Machine Translation Workshop, I sat down virtually with my former student, Alvin Grissom, where we talked about his prior work in simultaneous machine translation and the state of the field at the moment. I had a lot of fun chatting with Alvin, discussing everything from why I can't remember a phone number to racial justice. I hope you enjoy this as well. Please sit down with us. Thank you so much for chatting with me in the place of me giving a boring talk. One of the things that I've been encouraging my students to do is to try to turn what would normally be a one-sided lecture into an actual conversation, and hopefully that's what we can have here.
I'm very happy to be here. Thank you for inviting me.
Yeah, so who are you?
My name's Alvin Grissom II. I'm an assistant professor of computer science at Ursinus College. Soon, as in 2 weeks, I'll be an assistant professor of computer science at Haverford College. Both are in the Philadelphia area.
So what do you work on?
I work on a few things. Most recently, with some collaborators at UMass Amherst, I was involved in some work on trying to look at bias in extemporaneous speech in sports broadcasts for American football games. Before that, I was involved in a project looking at what we called pathologies in neural NLP systems, confidence in its predictions, and we explored some ways of mitigating this effect. And before that, and what I've done perhaps the most work in, or the most varied work in, is in simultaneous machine translation, which is of course what we're talking about today. And I was involved with He and you and some others on the first reinforcement learning based simultaneous translation system.
Okay, and that's what we're talking about today, since this is for a slot in the Simultaneous Translation Workshop. So what is simultaneous translation, and how is it different from normal machine translation?
Simultaneous translation is translation incrementally. So we don't assume, as we do in normal or traditional machine translation, that we have access to the entire sentence in the source language at the outset. So we translate as we're getting new words or morphemes or whatever in the source language into the target language.
Why is this more difficult than machine translation? Like, you go to Google Translate, you type in a sentence, it spits out a translation.
It's more challenging for a number of reasons. So at the most fundamental level, machine translation in the simultaneous setting is operating under imperfect information. With traditional machine translation, since we assume that we have access to the entire source sentence, you can think of this as a perfect information scenario. Whereas in the simultaneous setting, we know, or we assume, that we do not have all the information that we need. And so we have to make certain decisions under uncertainty, temporal uncertainty in this case, about how and when to translate this sentence that's still being formed as we're translating it.
You make a good point, and in some ways you could make normal machine translation even easier by giving it more context to disambiguate what topic you're talking about, or something like this. And so this is even more extreme, where you don't even have the full sentence, you just have a couple of words, and you still need to make some sort of prediction.
You mentioned prediction. One way you might approach translating such a sentence incrementally is to attempt to predict parts of the sentence that have not yet been seen.
So are there some language pairs that are more difficult to simultaneously translate than others?
Certainly there are. In fact, in our 2014 paper, the paper was called Don't Until the Final Verb Wait, because we were looking at verb prediction, and this was because we were working with Japanese, which is almost always verb final, and German, which is often also verb final, and translating to English, which is usually SVO, or subject verb object, where the verb comes between the subject and the object. And this is more difficult even in the non-simultaneous setting. So it's generally more difficult to translate languages for humans and for machines, to translate between languages that are more divergent, that are more different than it is between similar languages. But when you have missing information, it's worth asking, well, what information is missing? And in the case of going from a verb final language to a verb medial language like English, you're missing the verb. And so one of the things that you might want to, you have to deal with is, how do you make a sentence without a verb?
How can machine learning help?
Well, the approach that we came up with in 2014 was to use reinforcement learning to tackle this problem. So at the time, I don't believe that reinforcement learning was typically really used in the NLP world. But it seemed to make sense in this case because you have a situation where you are operating under uncertainty in a temporal domain where the words are coming in one at a time, and you don't know what to do. And so what machine learning can do is try to look for patterns. I am in a particular point in this sentence, and I've seen these words. So what should I do under in this situation?
Okay, so let's be specific. So how can computers help? What sort of patterns can they find, and how can that lead to something that might be better or complement what a human can do?
The work that has been done in areas like cognitive science can actually help us to frame the problem and give us some ideas about where we might look at work that's been done on human interpreters, studies that have been done on human interpreters. We know, for example, from some studies that humans seem to be predicting the final verb when translating between certain languages. We know also that in certain languages that the case markers seem to be very important.
So you said that humans predict verbs, but how is that possible? How can you figure out what a verb is going to be? What sort of clues do humans or computers take advantage of to predict what a verb is going to be?
The case markers in Japanese were very predictive. So this is a nice finding, I think, because it comports with some previous work by people in linguistics and psycholinguistics on the role of case markers in incremental language processing. We found that the case markers, when used independently as features, were very helpful in increasing the accuracy of predicting final verbs in Japanese.
We also saw things in other languages like German, so like the German verb for help, helfen, takes a dative object, and other verbs have reflexive markers as well. Thus far, we've been able to cover what is simultaneous machine translation, and the obvious comparison is to human simultaneous interpretation, as it's often called. This is a profession that requires many years of intense study. You see this at the highest levels of business and diplomatic negotiations. So is your goal to put all of these hardworking, well-educated people out of work?
Certainly not. I think there are settings in which such a system would be useful, but I think it's more useful to think about this in terms of assisting humans in some areas where perhaps a simultaneous interpreter is not readily available, or in a situation where perhaps a simultaneous interpreter can be helped by a system.
That's absolutely right. And in talking to simultaneous interpreters, one common thing that we hear again and again is that this is a really hard job, and they're paid very well because it's so tiring. And if someone is translating a conference, they can't do it alone. They usually work in teams and they switch out at 15 or 30-minute intervals. And so it's just too much for a single human to do at once, but maybe we could figure out ways to help people do the job where it's not so taxing. So kind of to that point, are there things that are really difficult for a human that are trivial for a computer, or vice versa?
For example, context switching, for handling the same kinds of situations over and over again, obviously. So, for example, if someone speaking uses some jargon or technical term, as long as that term or phrase is in the computer's translation table, or the computer algorithm has seen this at some point, the model has seen this at some point, it should be able to make a pretty good effort at translating it. And computers are very good at translating, for example, numbers, which can give humans quite a lot of trouble.
What about numbers makes them difficult for humans to translate?
So there are a couple of reasons numbers are difficult. To illustrate one of them, let's consider Japanese. So I can speak Japanese more or less fluently in many situations, but I still have trouble with numbers. And the reason for that is that in Japanese, when you go past 1,000, you start counting in increments of 10,000. So it can be quite taxing to try to do this on the fly. It's not even that easy to do it when it's not on the fly in many cases. So if you're trying to translate this potentially complex sentence, and then you have to do this kind of arithmetic in your head, it's quite difficult, and it could be very useful potentially to just have that show up on a screen for you, so that you can just look at the number and translate it in the language that you're translating to.
Yeah, absolutely. And forget about translating. I haven't known my phone number since grade school, and humans have trouble keeping large strings of numbers in their head, and let alone doing the manipulations to get them from one language to another. What about going the other direction? Are there some things that are really difficult for a computer that are more trivial for a human?
Humans are quite good at self-correction and inserting filler. Humans are good at creatively salvaging sentences that are partially complete but need to be reformulated halfway through them. And this is very difficult for a computer. Just fundamentally, for example, if you get the verb wrong in a partially translated sentence, how do you fix that? Humans are much better at making this feel less jarring than a machine system. We have a variety of social cues and tones of voice, disfluencies, all of these things to communicate what we want to communicate, even if it's not entirely fluent communication. If you look at a transcript, for example, of what you actually say in a conversation or in a speech, with all of the mistakes and ums and other oddities, corrections, most people will be surprised by how jumbled it all looks. But if you ask a person listening to you whether it was as jumbled as it looks on paper, they'll usually say no, because we just filter this stuff out when we're listening usually.
That's not to mention things like sarcasm or humor, where humans have an innate ability to process and correctly modulate so as not to offend, say, another head of state in a diplomatic negotiation.
That's right. So in a simultaneous machine translation or any simultaneous interpretation setting, the price or the cost of a correction is high. At best, you've introduced some awkwardness into the discourse. At worst, as you mentioned, you've offended some head of state. Humans are quite adapted to do this naturally in social situations, and it's very difficult for a machine to capture that kind of nuance.
So we've been talking about simultaneous interpretation of both humans and machines. And one thing that we need for machine learning is a reward function or some sort of evaluation. How do you know when a simultaneous interpretation is good?
So in 2014, we introduced the latency blue or L blue metric, which attempted to incorporate notions of translation quality and translation latency, where you're trying to minimize the latter and maximize the former, into the metric itself, which can then be used as your objective function.
Yeah, so let's talk about some of the alternatives. So you mentioned latency blue, which is this discrete integral over blue over the course of the translation. Gu et al. In 2017 had average proportion, which is trying to maximize the proportion of the sentence that you've covered, and so the higher the proportion, the better. Later, you have Liang Huang and other folks at Baidu introduce average lagging. So how do you compare and contrast all of these different alternatives for evaluating machine simultaneous interpretation?
I think that the difference between, for example, latency blue and average lagging, for example, is that latency blue is a sentence level metric, which, as you mentioned, is a discrete integral over the blue scores of the sub-sentence. Most of the lag-based metrics are usually separating the lag measurement from the evaluation of the quality, and when it comes to the quality, they fall back on the blue metric. That's not, or some other standard machine translation metric like Ribes or Rouge or Mint. And there's nothing wrong with that. That's fine. But I do think it's a difference.
I think the counter argument and why this has taken off is that this now gives you an additional knob to tune, and so there's an additional parameter. You pay the price for this, but you get more flexibility. You can trade off. I really want high quality, or I want as little delay as possible.
Well, with humans, one way of measuring their performance would be latency. I mean, you don't typically evaluate humans based on something like blue.
Yeah, and one thing that really surprised me is in talking to people at the University of Maryland's translation program, where they train simultaneous interpreters, is that a lot of this is standard public speaking. They score you on your poise and whether you use filler words, whether you correct yourself. Not a lot of it depends on how accurately you translate. They assume that you're going to get that right. So let's assume that simultaneous machine interpretation is a long way from being ready for prime time. What can we do in the meantime to know whether our attempts to help human interpreters actually are helping?
Well, one straightforward way is to, suppose you have some tool and you measure the performance of some pool of interpreters who don't use the tool and measure the pool of supporters that do use the tool, and you see if it helps.
I think one thing that you need to be mindful of is also looking at the cognitive load of the people doing this. And so maybe they do their job better, but it makes it much more stressful, and that might not be a good trade-off. Because simultaneous interpreters are so sought after, it's hard to get your hands on people to do these sorts of studies with. So a bit of self-promotion. A student, Joe Shoemaker, has been working on trying to create situations where crowd workers can do tasks similar to what a simultaneous interpreter does, but kind of abstracting out the training and years of preparation that goes into becoming a simultaneous interpreter, so that a crowd worker can do similar tasks with scaffolding that helps them get up to that level in contrived situations, that allows us to see whether, if we pop up potential translations for a word, is that helpful in doing something that looks and feels like simultaneous interpretation? There have been lots of paradigms for doing machine translation: rule-based, statistical, now neural. How do these interact with the simultaneous interpretation task, and what are the advantages and drawbacks to using each
I
of
think
them?
all of these have a place. So simultaneous machine translation, just as traditional machine translation started with rule-based systems, a statistical system gives us some other advantages. It's easier with Bayesian systems or statistical systems in general to get an idea of what it is doing and why.
You could also make the argument that in simultaneous interpretation you want high precision, and a rule-based system could have high precision. With the statistical framework, you can draw a lot of connections to the probabilistic interpretations that have come out of cognitive science for how people do prediction, and this ties into a bunch of proposals and frameworks for how people do the garden path prediction and things like this.
There's also a natural connection to work on, for example, paraphrasing and sentence simplification, that kind of work. Because in reality, interpreters are making compromises all the time. They're operating under incredible time and cognitive constraints.
I like seeing all of the different approaches, and I thought it was really nice to compare your work from 2014 with the Linajad et al. From 2018, and it's a very similar framework with the same state space, but what actually happens looks quite different because they're using an end-to-end neural system, and so it's amazing how big of a difference you can get by swapping out small components, and you have these cascade effects.
I think that's the way science is supposed to work. If it is the case that verb prediction is effective at helping simultaneous translation, for example, then hopefully we will see that in more studies.
That being said, one of the drawbacks of doing neural modeling is that you need really big data to train from, but we don't have a lot of data for simultaneous interpretation. We don't have a lot of recordings, and simultaneous interpreters are uneasy about having their unedited, uncorrected translations out in the wild. So it's hard to learn from the really seasoned experts that are out there. How can we get around this bottleneck?
What we did, so He was the first author on this paper in 2015. We used syntactic rules. So we would parse the English sentence in a Japanese to English translation training set, and then we would do transformations on those sentences to make the word order more similar to the word order of Japanese sentences.
So it sounds like this helps for simultaneous interpretation. Does it help for other things as well?
Yes, it turns out that due to the long distance reordering causing some problems for statistical machine translation systems, that this kind of reordering improves the performance according to standard metrics of traditional translation as well, not just incremental translation. So you get that as a bonus.
Let's start to wrap up. Where do you think the big challenges are in the near term for simultaneous interpretation?
So one is actually dealing with the speech aspect of this, which many of us don't really focus on right now. Another is the lack of training data. Beyond that, I would say the evaluation metric is a big one. Really, this field, I wouldn't call it nascent at this point. I've been glad to watch it gain some momentum recently. But it's still relatively early in this field. Machine translation is pretty old by computer science standards. And we only started using machine learning in 2014 with our paper for this problem. So that's 6 years. So we have a long way to go, but I believe that as more researchers work on this problem, that we'll get closer and closer to the kinds of systems that would actually be usable in a real setting. So I look forward to seeing that.
Yeah, going back to one thing that we talked about before, one thing that I'm really interested in personally is these human-computer collaborations where we can take the best of both worlds and combine the human ability to handle nuance and prosody and things like that, and combine that with computers' nigh infinite memory.
I think that's good for a couple of reasons. One, I think it's important that we create technologies, to the extent that we create technologies, that are actually helpful. It's also scientifically interesting because, as I mentioned, of the deep connections to cognitive science and linguistics.
These sorts of cooperative competitive frameworks, as we've seen from AlphaGo and things like that, are well suited for the application of reinforcement learning. So there are some interesting technical challenges here as well.
Definitely. It has been interesting to watch reinforcement learning gain popularity in NLP. As I recall, when we first were working on this paper, it was not a very common thing to see reinforcement learning in machine translation.
Yeah, and I remember spending a lot of time on the paper making the case for why we should be doing reinforcement learning and why it's not a completely crazy idea. Now you need to explain why you're not using reinforcement learning. Let's really wrap this up since it's getting late here in Europe. If anyone follows you on Twitter, as they should, and what's your Twitter handle?
Alvin, Grissom, I.
It's also clear that you're not just a researcher, but also passionate about social issues. As we're recording this in June 2020, is there anything you'd like to comment on?
Yeah, so I'm an assistant professor of computer science, but that's just one aspect of what I am or who I am. I guess I would say this is a really watershed moment. I'm not surprised by the protests that are occurring in the United States. It was inevitable. Even the vandalism was inevitable. There's not a people on earth who will endure what Black people have been enduring without occasionally lashing out, unless they are totally broken, and we are certainly not that. Even though this ostensibly has nothing to do with simultaneous translation, we all are involved in this system, this oppressive system. If you're not aware of that, that just means that you are comfortably situated within it. Being neutral is a tacit way of approving of the status quo. I guess I would also mention that the diversity in this field, while it's not the focus of these protests, everything is connected, is sorely lacking. It's highly unlikely that anyone watching this right now even has any Black colleagues. So everything is connected, and I just hope that people will think about this and pay attention and use this as an opportunity to educate themselves.
Well, we're just about out of time, but thank you very much, Alvin. I've really enjoyed talking to you. One of the things that I miss with virtual conferences is being able to talk to my friends and colleagues, and this is a nice way to kind of simulate that, and I always learn a lot from my interactions with you, so thank you again. It's been a pleasure.
Okay, thank you for this chat. It's been fun. I hope that others found it useful.